Okay, so good morning, afternoon, evening, depending on where you are in the world. So, as you know, we have been trying to put together a small module on life cycle assessment, and it's kind of within the context of decarbonization of urban transportation system. So, you must have seen on this website, on this web page, we have listed several reading material. We have also done some webinars and intensive courses, and this is a short-term module on life cycle analysis. So we'll get started with this one, and let me share my screen. Yeah. So I think you can see my screen now. So I'll get this slideshow going. Give me a second. Sometimes when you try to do things fast, it gets delayed, isn't it? So, okay, I think it should be up and running right now. Yes. Oh, nope, sorry. Yeah, it's there. Okay, so we are going to talk in this particular short video. We are going to talk on environmental release of chemicals and its fate and transport. See, when we're talking about life cycle assessment, ultimately what we are trying to do is calculate the environmental footprint. And when we say environmental footprint, of course, we are looking at impact. Of course, there is a, as per if you remember from that ISO methodology, we have goal and scope, we have function, functional units, then we have life cycle inventory, then we have life cycle impact. So impact is because of different chemicals getting into the environment in the solid, liquid, and the gaseous form. So here in this particular module, we try to give you a little bit of background on that, so that when when we're talking about the impact, you can relate it to that what the different methods are going to use, why they are doing the way they have done it, and how IPCC document has taken this the concept and try to put it in the broader framework of different impact categories. So let's start looking at in terms of the chemicals getting into the environment and what happens when the chemical gets into the environment. So material at the end of its useful life, at the end of the life, it gets released, and they may pose significant challenges. So now whether the chemical that gets released will degrade, or whether it will persist, whether it will be a longer period of time or a shorter period of time, what is the half-life, what is the degradation rates, these are all very, very important when you're talking about the risk from that particular chemical when they enter any environmental media. So when things comes to the environment, there are several processes which will happen. Like you will have dispersion, you will have dispersion of the chemical, persistent in the environment. Organisms can uptake it. Humans can take it through food and water as well, and it will may have a toxicity and the other health effects. So what are the relevant properties of that? For dispersion and fate, you're looking at volatility, whether it will go to the air, be it like a in the air media or not, density, melting point, water solubility, effectiveness of wastewater treatment, all those things are important in terms of dispersion and fate of chemicals into the environment. Whether it will be persistent depends on what will be the reaction rates, isn't it? Oxidation rate, hydrolysis rate, photolysis rate, rate of microbial degradation, rate of adsorption of that chemical contaminant, if they get adsorbed, sorry. Uptake by organisms, again, volatility, lipophility, molecular size, degradation rate, human uptake, transport across our dermal layer, against the lungs membrane, degradation rate within the human body. When you're trying to find toxicity, you're looking at the dose-response relationship, typical S-curve that people look at. So there are chemicals which persist in the environment for a long period of time. So, but when they are in the environment, they react with the atmosphere, different components of this atmosphere. When they are in the water environment, they have different rate of reaction in the aqueous environments. and it can be metabolized by different rates by the organisms as well. So if the environmental concentration, if you're looking at the rate of based on the release, and you ultimately, when you're looking at kind of cleanup or all that, you need to know how much of chemical is there where. So these chemicals and physical properties can be used to evaluate a variety of metrics. And some of those most commonly are persistent bioaccumulative toxicity. So we're talking about this like a gasoline spill. So you have this chemical sitting there, liquid gasoline, and it volatilizes. We know, so soil vapor through it will diffuse. If there is a crack here, it will also tend to go through the cracks into the building as well. So that's also possible. So it can essentially enter to the building through these cracks, which might be there in the foundation, or there will be, although it's not that soluble, but that it is at least a little bit of soluble, and that makes this dissolved plume going to the groundwater as well. So this is another example where you have a leaking storage tank, different things coming out. They're coming out at different rates. They're reacting at a different rate. So that's why you see a different kind of plumes coming out, contaminant leaking from a discharge site of radioactive waste right there. So this is another example. You have the leaching of the waste, putting into finally into the groundwater. So that's goes to the groundwater flow. And then you have reduced species. Like when you are looking at lower EH values or your lower ORP, things will move from your aerobic system to anaerobic system. So that's also kind of possible. So, and these are the properties which does affect, like melting point, boiling point, vapor pressure, Henry's laws, KOW, water solubility, soil absorption coefficient, bioconcentration factors. So all these things are coming. So using proper estimate to evaluate the environmental partitions, persistence, and measure of exposure. So we are problems associated with estimating environmental exposures, they are complex. So we need to find a relatively simple example of, so we'll talk about drinking water limit. Chemical say there is a chemical release into the river stream, into the public water demand. So what fraction of chemical will be absorbed by river sediments? What fraction will be volatilized? What fraction will take up by living organisms? What fraction of chemical will be biodegraded? What fraction of the chemical will be removed by the treatment system? So chemical and physical properties, they can be used to find the environmental footprint, use the values of property to directly categorize the environmental risk. So that is also kind of possible. So we look at based on persistence and bioaccumulation, something which is water solubility is more, it will tend to be in the liquid phase. If water solubility is less, it will tend to be in the non-water phase. Soil sorption, again, very strong sorption, it will tend to go into that. Into the soil, if it's no, then it will mostly be in the water. Biodegradation depends on the rate. Bioaccumulation potential, again, depends on octanol water coefficient and bioaccumulation concentration factor. So for each of these categories, a score must be given. So we look at a different score so that it becomes easy for us to kind of compare. So in terms of, if you look at fuel molecules, which is one of the major contaminants out there, as I have probably mentioned earlier, to the underground storage tanks, those petrol pumps or gasoline station, we call it gas station in some parts of the world, are pretty much leaking, especially when they're 40, 50 years old. And they tend to be a single group of single group of facility, you can say that, where you find a lot of problem in terms of contamination. So for example, here you look at ethanol. This is a water solubility. If you compare the soil sorption, water solubility, and biodegradation, when used in gasoline, ethanol, methyl MTBE, or isohexane. So you can use this data and then look at with chemicals. Isohexane is one of the most commonly used molecules. Ethanol is commonly obtained from corn grain. So, and then also butylene is there, methanol is there. So based on there, you know the soil sorption, you know the water solubility, and you have the biodegradation rates. So you can say that if petroleum-driven gasoline is spilled onto the ground, more likely to be absorbed than soil. So ethanol probably ethanol will probably get absorbed. Salt sorption is less actually. MTBE salt sorption is more. Isohexane is also more. So it's if it is more likely to absorb the salt than MTBE in ethanol. Yes, if isohexane is there, less likely to migrate to the water sources because the solubility is low. Where the MTBE methanol have because of they may design. In contrast, our MTBE and ethanol have been added to gasoline because of clean air. Ethanol and MTBE are more likely to find their way into the surface and groundwater. So because of the Clean Air Act, so it's kind of interesting. So because of the Clean Air Act, we have introduced this MTBE in ethanol, but MTBE in ethanol could become a more of a like a surface water and a groundwater problem as opposed to this being the air problem. So that's interesting. So depending on where you are, what is your focus? Sometimes you're solving a problem, but the other problem you are, I'm not saying you're creating another problem, but you're creating certain scenarios which could be of a concern. So there are people talk about green sustainable material. You have to use material as an engineer or a scientist. So materials footprint is important. So material has to be extracted, then enters the product system, reduce, reuse, recycle, those kind of stuff. So in terms of material extraction, you have to get the raw material, the ore, then extraction. Then you have to do footprint associated with extraction. So it's an energy intensive process, whether it's an energy intensive or water intensive process. Most common elements, which is kind of the oxygen, silica, aluminum, iron, calcium, magnesium, and potassium, they're the most common. Present in greater than 1% abundance. Then we have silver, tin, and bismuth, which is very low. So this is your abundance of the selected elements in the earth crust. Different figures, don't have to remember those, and this is annual production of elements. So you can see that the ones which is higher in abundance, probably easier to extract, and that's why you see them both being more. So if you look at earth crust, if you have to do this, for example, supplies and use of elements. So if you are looking at like Earth, assume an approximate mass of the crust is 2 times 10 to the power of 19 metric tons. This mass is based on 40 kilometer thickness of continental crust and 3 kilometer thickness in oceanic crust. Average density is 3 grams per centimeter cube, which is like 3 tons per meter cube. So for that, you have the abundance, you find out how much tons per year. So the ratio of abundance to use, that is we can use is abundance is given to us 5.6%, use is 120. So ratio of abundance to use, so that becomes like 1 times 10 to the power 19 and all those numbers. The present scenario, all material present in the crust can be extracted. Not all material can be extracted, concentration too low. This is so you have the total crust abundance, economically extractable deposits. That's what I talk about. Okay, so relationship between total crust abundance and the reserves. So abundance in the crust on the y-axis and the reserves on the x-axis. And as you can see, there is some sort of positive correlation there as well. Like higher the reserves, higher the abundance, more the reserves you see too. Economically extractable, people talk about resources. The resources might be there, but how much it is will be taken out. So I'll calculate the ratio of Earth. So here you have economically extracted resources, 230,000 million or whatever, so much of that. And then you have nickel, zinc, and all that. So in terms of tons per year of use, so we have that data as well from the previous one. So say for iron, ratio of abundance is whatever is available divided by how much is being used. So for iron, we are looking at 191 years. But for something like antimony, bismuth, silver, we are looking at 17, 10, and 20 years. So what does it mean? We cannot really go and do mining forever. You have to start recycling, use secondary material. So although total amount of material is available, but we don't know whether they will be, it's present in high enough concentration to be economically recoverable. So that is also important. So there's something called Sherwood relationship. So it's the cost of a material is largely determined by the cost of extracting and purifying the raw material. So relationship between the prices and dilution. So Sherwood is a technology dependent. So this is your Sherwood dilution and prices. More is the kg over per kg metal. you better more your like a price, more ore you require to process. In here for energy burden, so you have to look at the delta S, the entropy of the missing system. So go into the basics of those entropy and Gibbs free energy, delta G is T delta S, so which we all kind of learned about it. So here if you look at an example, fuel is $3. Each gallon contains approximately this much of BTU. So what is energy for 1 kg of metal at room temperature? So that can be solved. Then economically recovered reserve. So reserve is there, but how much is can be economically extracted? So that is also important to have a look. So for cumulative, there are indefinite identified sources, and there also would be undiscovered sources as well. So demonstrated, like measured and indicated, then you have the inferred ones. So economic, we have reserves, marginal reserves, demonstrated sub-economically resources. Then inferred, you have inferred reserves, inferred marginal reserves, and all that. And so other occurrence includes non-conventional and low-grade materials too. So that's your other occurrences that you kind of see over there. So reserves that are known and their extent demonstrated can be recovered, referred to economically recoverable reserves. Marginal reserves are the cost-effective, either moderate improvements in technology, and unlikely to be reserved. That's a sub-economic. So those are the different kind of reserves. Supplies of elements, you look at infinite, ample, adequate, potentially limited, and potentially highly limited is silver, gold, copper, and all that. So that's okay. So in the engineered system, material has a life cycle. Material comes in, they flow through the system. So you have the domestic extraction, import, then goes through a accumulation in the system, then output, you have emissions coming out, then of course you have the exports also going out. So you can do what is known as the material flow analysis. For example, for lead is a neurotoxin, is associated with development delays. So some lead has been an octane enhancer in gasoline and in batteries and paint. So you can come up with a material flow diagram of a lead. So this kind of diagram, that how much lead is coming in, where it is being used, what is happening with that lead. So you're looking at different stakeholders, as you can see, primary production, import that is coming in into the product. There are a variety of products out there. So that could be prepared from those the material that you have. And so in terms of this, again, I'm not going to read that. The PDF is available to you. You can read it. So it's just basically kind of giving a big picture overview of the lead, the figure that you just saw before, how the things have changed for lead as an element. So similarly, you can have a similar diagram, slightly less complicated diagram for iron, where you can again kind of you can look at how the material is moving in different phases and what is happening to them, how they are being used, and all that. Okay, so we can look at different types of flow types and all those stuff. So that's fine. We can look at global material balance. So this is what flow of iron in United States. We can have a similar diagram for, say, in India or whatever country you are from. So flows of iron in China is given. Importing, exporting, how much iron is being imported and being exported. So in terms of export, Australia, Brazil, Russia, Canada, Romania, they do a lot of export. Import, those again, you see, Canada also sometimes exports quite a bit. Belgium, Czech, Austria, Poland, Netherlands, UK, France, Germany, all these things, they are both they are importing as well as exporting, and there is something called net exporter. So many of these, the dotted line that you see, they seems to be net exporter. So that's what we looked at earlier. So percentage, how much percentage is theoretically recoverable and how much percentage is being recycled? It's pretty low. So we need to kind of go up. It's very, very low. Our kind of recycle, percentage recycle. So so this is some kind of analysis in terms of recyclables. You can go in this, the book is listed there. You can go and look at one of these books, and I think books is also kind of copied here on the last slide. So books details. So United Nations has more recent global data on metal recycling. When I say books, it's mostly the reference material. It's global recycling rates can continue. Metals like lead is getting into there. Primary barrier used as a raw material, lack of critical information on waste stream. They lack critical information needed to assess whether the stream might be reused. So we have to basically maybe create some of those data. Problem energy savings due to recycling. Like we are looking how much energy is saving due to recycle. So you are looking at this much kilowatt hour, then so this much of kilowatt hour, this much of point compared to uh, this is for indirect production factory. And so this is basically looking at the aluminum in terms of energy input required for 1,000 pounds of primary aluminum production, and then energy required for 1,000 pounds of recovered. So as you can see, recovered is 303 kilowatt hour, and where the total for the virgin one it was 7,240 kilowatt hours. So you're saving a huge amount of energy by doing that. So in terms of material flow, which is kind of important when you talk about life cycle, you need to look at where the material is coming from, where it is going, what kind of a mining operation, what is the environmental footprint related to those mining operations, and when you are going to use it, what is its intended application, how it compares with other peers in terms of different papers and other things which is out there, if it is out there. And we may not be exactly on this topic, but something similar to this topic might be available. So those are the things I think we need to kind of consider on this aspect. So summary, almost engineering design involves use of material. So this particular module summarizes the method for characterizing the footprints. Is the material scarce? Can it be recycled? Do environmental release have significant impacts? Engineers need to consider materials in the context of product design, recognizing that the choice of the most sustainable material will be application specific as well. So thank you. So this kind of gives us this is the last lecture for the module 1. So I hope your have these things are being useful for you. So thank you again, and I'll see you in the next like a module 2 videos. Thanks. Okay, so we can stop.